Regular languages are closed under the union operation. What do I mean by this? What I mean is that if you have two languages, L1 and L2, that are both regular, then their union, L1 union L2, is also going to be regular. Okay. Now, once again, I'm going to do the same thing. What is given to me and what do I need to derive? What's given to me is two regular languages. So I know that there's a DFA M that solves L1. There's a DFA L2, M prime that solves L2. And then the goal is to construct a DFA, let's call it M double prime, to solve L1 union L2. So you can write this out, right? So this is like the first paragraph of your proof. At this point, you have no idea perhaps how to figure this out. You don't know how the proof is going to go, but at least you know how it starts, and this is how it's going to start. And once again, I think it's very reasonable to expect that this is going to be a proof by construction, like a direct proof, just like we did before. And of course, M double prime, the construction of the M double prime, will depend somehow on the DFA's M and M prime. Okay, good. So now this is the task at hand. Okay, so now what do you do though, right? I mean, how do you construct this DFA M double prime? It's not immediately clear at all, right? In the previous case, I think we had, more clear vision of what to do, but here it's not as clear. So then we have to really reason through this slowly. Okay, now how can we do that? Well, recall a DFA is what? A DFA, as I said in the last lecture, is a very restricted programming language in some sense, right? You can think of it that way. And if you think about like a programming task, maybe you're taking some intro programming course, you're learning how to like write Python code, and in the homework you're given some problem and you need to solve some task in Python. Like as a teacher, what I would recommend to you is I would say, look, forget about Python, forget about the syntax, and think about how you yourself would solve this problem, okay? Imagine you have some long input. What would you do to determine what the solution to the problem should be? Now, once you do that, if you can do that, then you've done the hard part in some sense. You've done the creative part, and all that remains will be to take what you did and transfer it into Python code. Now that step can be a bit difficult if you're not used to the Python syntax, but if you are used to Python syntax, then that step actually is the much easier part of the process. Now, given that DFAs are just some restricted programming language, you can do the same thing, right? I'm gonna recommend to you that in situations like this, imagine yourself as a DFA and ask, how would you yourself solve this? Okay, so here's the mindset that we want to follow. Step one, imagine yourself as a DFA. Now, since DFAs are like a limiting computational model, of course you want to apply the same restrictions to yourself as you're thinking about yourself as a DFA, right? So what are those restrictions? What are the rules that you need to follow? For one, you have to scan the input only once from left to right. Okay, so you have to follow that rule. And two, you can only remember constant amount of information, right? So you only have constant number of states, and the only way to remember stuff is really through the states. So that kind of means basically that you have constant amount of information, where constant means cannot change based on the input length, right? So no matter what input length you have, whether it's like 10 symbols long or 100 or 1,000,000 or 1,000,000,000, the DFA only has a constant number of states, a fixed number of states, and that's all it can use. Okay, so that's what it means to have constant amount of states, constant amount of information to work with. Good, okay, so we're gonna apply these restrictions to ourselves and try to come up with a solution. But then, once you do this, I would claim that most of the time you're 80%, 90% done, right? Because the next step is going to be basically now define yourself as a DFA, right? Write down yourself as the 5 tuple of the DFA. What's your set of states? What's your transition function? What's your starting state? And what is your set of accepting states? that part is not really the creative part. The creative part is step 1. So, and step 2 is really like, putting down everything using mathematical notation. Now, that can be difficult and that can be challenging at first, okay? So if you're not used to mathematical notation and if you're not used to that process of going from like ideas down to mathematical notation, you might find that challenging, and that's completely fine, right? Don't feel bad at all if you find that challenging. But nevertheless, you should know that, that is not the creative part. That's just a matter of getting used to, okay? So you just have to spend the time, get used to it. And once you're used to that, then you'll see that, it's relatively straightforward. So really step 1 is the important part. Good, so now let's do this, right? We're gonna come back to our, union example that we're trying to do. So we're gonna imagine ourselves as the DFA. Now, how can we do this? Well, another, tip that we recommend, another thing that we recommend when you're trying to solve a problem is to work with small examples to build up your intuition, okay? And this is exactly what I want to do with this one. I want to actually define some languages, L1, L2, just some small examples, basic examples that I can work with, and see then if I can find a construction for their union. Okay, so my first language is going to be L1, strings with even number of ones, and L2 is going to be strings with length divisible by 3. Okay, now let me actually draw the DFAs for these ones. Okay, so this is the DFA for L1, and here's a DFA for L2, this M prime. Okay, good. So we have these DFAs, and now I'm going to ask you, right, like what is our task first of all here, right? So we want to construct a machine that decides the L1 union L2. So we're imagining ourselves as like, the DFA. So our task really is given a word, given a string W, we want to know, is it in L1 or is it in L2? If it's in one of them, then we should accept. And to now figure out whether it's in L1, L2, given that we have these DFAs, what would you do? Well, a natural thing to do would be I'll run it in the machine M and see where it goes. I'll run it in the machine M prime, see where it ends up. And if one of them accepts, then I want to accept, right? Now, what's the problem with that? What's the problem with, the strategy that I just described? Yeah, I have to now remember that, look, I have some restrictions that I have to respect. One restriction is that I can only scan the input once. And the way that I just described to you, it would require 2 scans, because I would have to first feed it through M. So that will be 1 scan. And then I go back and feed it through M prime. That will be the 2nd scan. So I can't do that. Okay. So then what should I do instead? What can I do to fix this? Yeah, I'm saying, can we merge DFAs, duplicate the digits, read them simultaneously? Yeah, so that's a nice idea, right? If I could, so what I would like to do, I have the input, I'm going to scan it once, and if I could now somehow simulate both machines at the same time, right, then that would work, right? So why not try that, right? As we're scanning, let's try to simulate both machines at the same time. In programming lingo, you would say open up 2 threads, 2 separate threads, and run them together. So let's see how that would go, okay? So here's a sample input, 101, 001. I have 2 threads. One thread, this is thread 1, is going to keep track of the first machine M. The second thread is going to keep track of the second machine M prime. And then we'll advance both machines at the same time. So initially we start at the starting initial states of both machines, right? That's P0 and Q even. Now here in my table, I'm denoting Q even by QE because I don't have quite enough space here to write it all. So QE denotes Q even. And then when I read the first symbol, right, That takes me to Q odd. So here I have Q sub O. So again, this is a shorthand for Q odd. So every time in the first thread, every time I read a 1, I go to the other state. I switch states. And thread 2, every time I read a new symbol, doesn't matter whether it's 0 or 1, I will go to the next state. Okay, so that's after one step. So after reading another 0, then I'm going to stay at Q0 here, and then I'm going to be at P2. After another one, then I'm at QE and P0. Another 0, QE and P1. Another 0, QE, P2. And then finally QO and P0, right? And then I'm done with the input. Now, what's the decision going to be? Right, so I'm going to be checking here among Q sub O and P0, is one of them accepting, right? So in this case, we see that P0 is accepting. And since one of them accepts, the decision should be to accept, right? So in general, if at least one of them accepts, then we accept. If both of them reject, then we would reject. Very good. Now I have to ask, okay, I did this process. Did I respect the conditions, the restrictions of a DFA as I was doing this, right? So the first question is, are we scanning the input only once? Or did I scan it more than once? No. I mean, I did indeed scan it only once. So that's good. So that we respected. Second question is, do we need to remember more than a constant amount of information? Well, what are we remembering at each unit, at each symbol? Well, we are remembering one state from the first machine and another state from the second machine, right? Two states. And now the question is that a constant amount of information, or is that something that needs to grow as the input grows? What do you guys think? Right? It's constant, right? It doesn't matter if the number of symbols I had here was 6, but it doesn't matter if I had 6 symbols, 100 symbols, 1,000,000 or 1,000,000,000 symbols. No matter what, I'll only need to remember one state from the first machine, another state from the second machine. And that's constant. That does not grow with respect to input length. So now at this point, I feel great, right? Because now I feel like I'm basically done with step 1. I've convinced myself that this can be done using one scan through the input and only remembering constant amount of information. So I know that there's a DFA for this. Now the second step will be to actually write this down formally and define myself here as a DFA. And we'll do that. But before we even go there, let me spell this out even a little bit more. Let me even draw out the DFA for this particular example for you. Let me draw out M double prime and what it would, and so you can see what it would look like before we even define the DFA formally. Okay. So the main idea here is construct a single DFA, which is going to be M double prime, that keeps track of both M and M prime. And now, how many states is M double prime going to have? We're going to have 6 states, right? Why? Because it corresponds to, every state corresponds to a tuple of states. The first coordinate comes from the first machine, the second coordinate comes from the second machine. The first machine has 2 states, the second machine has 3 states, so in total we get these 6 states. Good. What is the initial state here? Which one should I label as the initial state? Right, Q even P0, you got it. Why? Because Q even is the initial state of the first machine and P0 is the initial state of the second machine. Which ones should be the set of, which ones should be accepting states? How can I determine the accepting states? Yeah, correct. So if one of the coordinates is an accepting state of the corresponding machine, then I should be actually accepting. So in this case, what does that mean? We know that Q even is an accepting state of the first machine, and we know P0 is an accepting state of the second machine. So that's why if the first coordinate is Q even, we are accepting, and if the second coordinate in addition, if the second coordinate is P0, then we accept. Good. Now, what about the transition function? So if I were to, for example, look at the initial state and I want to know where will the zero transition go from the initial state, how do I determine that? What would I do? Well, what I would do is I would, advance the first coordinate, q even, according to the transition function of the first machine, and advance the second coordinate according to the transition function of the second machine. Right? So we know that 0 actually does not change the state of the first machine, so that will keep q even. But no matter what we read in the second machine, we go to the next state, so p0 should become p1. So that's why this goes to q even p1. And if it was a 1, then in this case, q even would become q odd, and p0 again would be p1, so we would go there. As another quick example, if we were in q odd p1, well, the 0 doesn't change the first machine, so that's going to stay q odd, but p1 will become p2, so that goes there. And then if it was a 1, then we know q odd is going to become q even, and p1 is going to become p2, so that goes there. Okay, and you call like this, and then voila, you have all your transitions, and here's the full complete DFA picture for you. Now, this kind of looks complicated. I mean, lots of arrows flying around, but hopefully you agree that the idea behind the construction is relatively simple. And and then you can simulate this machine now, but this is basically the DFA for the particular example L1, L2 that we had, and M and M prime we had. And now, we feel great about this, and all we need to do is now define formally M double prime. Okay, so let's write this out, formally defining the union construction. So we will be like, okay, let M be the DFA, let be a DFA solving L1, let M prime be a DFA solving L2, and then now we construct M double prime solving L1 union L2. And then we specify now each component here. So what's going to be Q double prime? So who can tell me how we're going to define Q double prime? Of course, we're going to be making use of M and M prime here to define the components of M double prime. Right, exactly. I mean, we have a tuple, as we said. First coordinate comes from the Q, capital Q, and the second coordinate comes from Q prime. Right, so we can write this, the set of all tuples where the first coordinate comes from Q and the second coordinate comes from Q prime. That can be written using the this notation here, as you can see, Q times Q prime. But you can also write it in this following way, using set builder notation. It's all those tuples Q comma Q prime, such that Q is in capital Q and Q prime is in capital Q prime. Good. Now the alphabet is the same, so we don't have to define that. That's the same sigma. Now we go to the transition function, delta double prime. Now the signature of the transition function is, just like we've seen it before, the transition function is always, of the form Q times sigma to Q, but in this case, our Q is Q double prime times, the alphabet, and map is set to another state Q double prime. But we know Q double prime is Q times Q prime, so I could also write this if I wanted in this manner. It's the same equivalent way. Now, when I want to define a function for you, how do I define it? Right? How can I define a function? What's the way to specify what the function is going to be? We have to do what? Yes, so you have to basically, for each input, you have to tell me what the corresponding output should be. Once you do that, you define the function. And a way to do that would be to say, okay, let's consider some arbitrary inputs. So take some Q, small q in the capital Q, some Q prime in capital Q prime, and some symbol, small sigma. So this is like in Greek, this is small, this is capital sigma, this is small k sigma. Some sigma in capital sigma. Okay, so these are all in some sense arbitrary variables now, denoting arbitrary elements of these sets, and then now define for me what the function should be, right? So what it should be delta double prime, right? Now this is q prime, this is the state, and then the symbol. Right. Very good, right? So I'm seeing the right answers here. Probably I need to go smaller here. Right, so what you do, the idea is basically you advance the first coordinate according to the transition function of the first machine, and you advance the second coordinate according to the transition function of the second machine. So if you put that in notation, that means you apply the first transition function delta to q and sigma, and then the second coordinate, you apply the transition function of the second machine, delta prime, to q prime and sigma. Okay, and then this is your new state, the tuple that you have. Good. And then we're almost there, right? So then we're going to have q0 double prime. What is this going to be? We already seen it in the previous example. The initial state is just going to be consisting of the initial state of the first machine and the initial state of the second machine. So that's q0 and q0 prime. And how about the set of final accepting states, f double prime? Yeah, so f q prime, f times q prime union q times f prime, f prime union f, f union f prime I'm seeing. So that's actually not going to work. Right, so why does not, so f, so I'm seeing like, for example, f union f prime. Does this type check? Right, so you have to remember that, oh, the set of states of the new machine is consists of tuples, right? So this is not a set of tuples, so that doesn't work. And f, this will also not quite work, right? So I think you guys are making it a bit more difficult, maybe trying to get like a concise Cartesian product representation here. I think it's much clearer to use just a set builder notation. And when I write it in set builder notation, I think you're going to see that it's clear that it's correct. So it's the set of all those tuples, right? Q comma Q prime, where either Q is an accepting state of the first machine or Q prime is an accepting state of the second machine, right? So I hope that, you know, in this notation, it's pretty clear. You can write it in terms of Cartesian product as well and the union. That's fine. But I find that this is actually clearer. When you read this, I think you're like, yeah, of course, that's the set of accepting states. Okay. Now you've defined the DFA M double prime, and now you might be like, okay, what do I need to do? Well, maybe it remains to show that this is indeed a correct DFA that actually solves the L1 union L2. So you might go about this by proving a double containment, doing a double containment argument, and finish the proof like that. Now here's another question. I mean, we had this question in the previous one, and I'll ask again, actually. Is this part necessary for the proof? Or can we just say, look, here is the DFA M double prime, and we're done? Depends on the audience. Very good. I totally agree with that. Necessary, not obvious. Correct. Yeah. So here is my answer to this. It depends. It depends on what you have done before, basically. Okay. So if this is your proof, right? So you start by like, oh, let M be the DFA for L, let M prime be the DFA L prime, and here's the 5-tuple representation of M double prime, and then bam, that's it. Then I would say no, that's not okay, right? Because you didn't explain anything, you just like constructed something and you're just claiming that this works. If on the other hand, so in that case, I should say, in that case, you have to write down these arguments right here at the end. If on the other hand, you had like a very nice explanation, like just the way maybe, we did, we reasoned through it and we said, look, the idea here is to really have two threads and run these machines simultaneously. And then the way to do that would be to like have a tuple of states, one for the first machine, the second is the second machine, and then you advance the first coordinate according to the first transition function and so on and so forth. So you give all that explanation, then I think, you do that and then you give this construction, then that's pretty convincing in my opinion, right? So if I read that, I'm going to be like, yeah, that makes total sense. You got it, right? But as I said, if you don't do any of that explanation and you're like directly, oh, here's the 5, tuple definition of M double prime, that's not enough. Okay.